Hi folks, this is my second lecture about kinetics, and today we are going to talk about the differential rate law, which is often only just called the rate law, which is confusing because there's another kind of rate law which is always called the integrated rate law. But today we're talking about the rate law, which is the differential rate law. And here is your assistant chicken, the chicken of kinetics. Hello. So here we go. The differential rate law is a rate law that looks like this, and you've seen something like this last lecture when we were talking about the mechanisms. And what it relates together is how does the rate get affected by the concentration of your reactants. And you can look at how fast the reaction goes based on fiddling with the concentration of the reactants. You go, if I increase this, does that increase the rate law linearly or squaredly or not at all or whatever? And we were looking at the differential rate laws for elementary steps for each individual step. This has the same structure, but it is the overall rate law, which is what you base all of your stuff off of. So this K that you've got is the rate constant, and as is the case with many constant things, it is constant for a particular reaction at a particular temperature. And the way that you figure out what your rate law is, which is really important, is by doing it in lab. You can't just look at the reaction and guess what the rate law is going to be based on, oh, well, I figure it'll be like this. You can't do that. You have to actually run the experiment of, running the reaction and then changing the concentration and seeing what the effect is, and then changing the concentration of the other thing and then seeing what the effect is. And that data is what you use to figure out what your rate law is going to be like. And once you've gotten that rate law, you can use that to sort of figure out maybe what your mechanism is, which is what we talked about last time. But we are going to learn how to do a method of initial rates type of problem. And the concept of the method of initial rates problems is this. Let me show you. Let's see, do I have one? I think all I have is the back. We can do this. I'll flip over and do that problem after we talk about this. The method of initial rates is this. The reason that it's called the initial rate is because you're running this reaction for a relatively brief period of time and measuring the reaction rate. And the way that you measure the reaction rate is to measure the disappearance of your reactants. But you can't really run that reaction for a really long period of time, because what happens is your products will build up. And if you're dealing with a reaction that has an equilibrium to it instead of going to completion, if your products build up too much, it'll start shifting back towards the left, and that'll really screw up your reaction rate readings. So that's why this is called the method of initial rates. You only run this for a brief period of time, and then you kind of quit. So let me flip over here to this back of this page of notes. So this is what a method of initial rates problem is going to look like. And what they'll do is they'll give you the reaction itself, and they'll say, here's your reaction. You've got bromate and bromide and protons reacting together to give you elemental bromine and water. Okay. And so you're wondering, well, gee, is the bromate really important for the rate, or is it the bromide, or is it the protons? So what you do is you run 4 experiments, and in experiment 1 versus experiment 2, you can look at the concentrations of the things and you can see what the scientists decided to do. They set all of the concentrations of the 3 reactants to 0.1 molar, 0.1 molar, 0.1 molar, 0.1 molar, and they let it run, and then they measured what the initial rate of the reaction was, and that was 8 e to the negative 4 moles per liter per second, which is molarity per second. And that might be and they didn't actually say, this problem doesn't actually say. So the initial rate here is, say, the disappearance of one of these or the appearance of one of these, but it doesn't really matter in this question because all you want to do is compare it to a different experiment. So that's experiment 1. With experiment 2, what they did is they held the bromide and the protons constant, but they doubled the bromate. And so the comparison between experiment 1 and experiment 2 is, well, gee, what happens when I double bromate? Does it matter? Does it matter linearly or does it matter squared? Which means, is it zeroth order for bromate? Is it first order for bromate, or is it second order for bromate? And so what you do is you go, okay, well, from point 10 to point 20, that's a doubling. Let's see what happened to the rate. From 8e to the negative 4 to 1.6e to the negative 3 is a doubling. So when you double, it doubles. That is a linear increase. So that means that what we have determined is that bromate matters in the rate law in a linear fashion. So that means that it's first order. If it had been 10 to 20 and it quadrupled, so you doubled this one and you quadrupled the rate, that would be squaring. So then you would be able to tell, so if it would have gone from 8e negative 4 to 3.2e negative 3. That would be a quadrupling when you doubled, and so then you could tell that, oh, well, it was squared, so that means it mattered more, so that means that bromate would be a exponential or a second order overall. So that's what you do, and we're going to come back and do the rest of this problem, but that's the idea behind, that's not where I want to go, the method of initial rates. So let's go back up. Yeah, so the answers that you can figure out from the method of initial rates is that you could figure out that the concentration of your reactant doesn't matter, which means that if you double its concentration, the rate stays the same. It can be first order, which means that it matters linearly, which means if you double the concentration, the rate doubles. That's a linear increase. Or it can be second order, where if you double your concentration of a reactant, then the rate responds by squaring, or in this, because you've doubled it, quadrupling. If you did tripling, then it would square that, so it would be 3 times as much versus 9 times as much. That would be another one. So you have to look to see if it's linear or exponential. So those are the 3 that we really deal with. There are other orders. There are bigger orders. You can have a mechanism so bizarre that something can be third order or fourth order. You can even have fractions where the concentration matters, 2.5 times, and then that would imply that the mechanism was sort of way more complicated than you knew. So don't, sometimes you'll see a question that's like, is it possible to have fractions? And most people would say, oh no, I've never seen a fraction. The reason that you've never seen one with a fraction is because it's sort of too complex for us to have to deal with, but they do exist. And then another question that they'll ask is, what is the overall reaction order? And the overall reaction order, each of these, so here's an example of a rate law, a differential rate law. The order for A is 2. The order for B is 1. So it's first order in B, second order in A. The overall reaction order is 3 because you add up the 2 exponents, the 2 and the 1. Same deal here. In this one, rate equals K, A, B squared. It is first order in A, second order in B, and third order overall. If it was squared and squared, it would be fourth order overall, etc. Okay? Alright, so that's a differential rate law, and that tells you what the concentration has to do with the rate. Now we're going to talk about the units for this, which the units for this are really important, and also if you have a good handle on the units, they can sort of help you cheat a little bit with questions, because you'll sometimes get a multiple choice question where they will say they'll give you all this information to make you work a problem, but they'll give you K, and they'll give you K's units. Well, K's units give away the answer, because when you have to work out what the units for K are, you do the algebra, you get K by itself, so you end up with rate divided by all of this stuff. And the units for rate are moles per liter per second, so that's rate. And so seconds is on the bottom here, by the way. It doesn't look like it is, but it is. So that's moles per liter times seconds. When you have B, for example, that is first order here, the unit for B is moles per liter, which is sort of normal. When you're dealing with a squared or a second order reactant, you end up with moles per liter times moles per liter. So you have moles per liter squared. And so what ends up happening is, to get K by itself, you divide moles per liter per second times some number of moles per liters, and you end up canceling moles per liter a couple of times. So let's sort of see how it goes. There's a pattern. When the reaction order is 0th, 1st, 2nd, 3rd, you can watch that the moles units go from 1 to 0 to -1 to 2. So 0, 1, 2, 3, 1, 0, -1, -2. So it's decreasing starting at 1. Liters goes -1, 0, 1, 2. It's increasing liters. Seconds always stays -1, -1, -1, -1. This is because of what is happening in the cancellation of the units. So when you have a zeroth order reaction where the rate equals K times nothing at all, because none of the reactants change the rate, you've got the units here that cancel out, where moles per liter per second equals K. So the units for K are moles per liter per second, which is moles on top, liters on bottom, seconds on bottom. Pew! That's easy. So that's zeroth order. First order, you've got moles per liter per second for the rate, you've got K, and you've got moles per liter for this A here. And what you're going to do to get K by itself, which is how you get your K's units, is you divide moles per liter. So that's going to cancel this mole and cancel this liter, leaving you with only the seconds. So for a first order reaction, if they tell you that they will tell you that K's unit is seconds to the -1, you can tell that it's first order, because moles is 0 and liters is 0. When you get to a second order reaction, you've got rates units, which are moles per liters per second, and you've got K, and you've got A squared. So the units for A are moles per liter, but it's squared. So what you end up doing is you cancel one of the moles per liters, and then the other one you divide over, and because you're dividing, it flips upside down. So you end up with moles on the bottom, that's the -1, a liters on the top, and seconds to the -1 is always on the bottom. So there you go. So that's canceling one of the moles per liters, and the other one ends up flipping. When you get to the third reaction order, when you have a third order reaction overall, when you've got an A and 2 B's or something like that, the moles per liter of the rate cancels with one of the moles per liters, but there are 2 others that don't get canceled, and so you end up with moles on the bottom twice, moles -2, liters on the top twice, liters squared, and again seconds to the -1st. So all this to say, it's really helpful to have an understanding of K's units follow a pattern, and if you actually have the pattern memorized, you can skip a lot of work. All right, So that's differential rate laws. For every order of a differential rate law, there is a matching integrated rate law. And we have a chart that has them paired together that I want to show you that's really important. Is a really important chart. It's this chart, but I made it bigger so that I can talk about it better on the screen. Come here, chart. All right. So here we have zeroth order, first order, and second order overall reactions. And here are the rate laws, which they left off the word differential because they're being difficult, but that's what they do. These are the differential rate laws, which is showing you that the rate is equal to K times some exponent of your concentration. So for zeroth order, A doesn't matter, and actually this is a 0, so that's not really there, right? Because anything to the zeroth power is 1. For first order, rate equals k times a linearly, so it's to the first power. For second order, rate equals k times a squared, and so it's exponential. So that's your differential rate law. There, for each of these, for the zeroth differential, there is a zeroth integrated. These are a pair. They're a team. So rate equals k matches with this integrated rate law. Rate equals ka matches with this integrated rate law, the one with the ln's, the natural logs. Rate equals ka squared matches with the inverse one here, 1 over a and 1 over a. So it's really important for you to know who partners are. And you've got to have that down. So this is zeroth order, that's zeroth order integrated. This is zeroth order differential, this is first order differential, this is first order integrated. This is second order differential, this is second order integrated. You've got to have that all together in your head. Also, there's a graph that goes with it and a half-life expression that goes with it. And you've got to have kind of all of this information together in your head, kind of as a team of 4 helpful things. Yeah, that was a great word. So let's look at this integrated rate law and talk about what it is telling us. Where the differential rate law is saying, hey, this is what changing concentration does to your rate. So it's concentration versus rate. The integrated rate law is telling you what happens over time to your concentration. So what it's saying is, here's your initial concentration, A0. And if you're wondering, gee, what's the concentration now? Your concentration now, A, at time t, is equal to negative k times t plus A0. So however much you started with, and however much you've lost so far, which is your rate constant times however much time there has been. So that's a very simple formula, and what's nice is that you may recognize this from math class as following the same structure as y equals mx plus b. Oh boy, that's the kind of thing that we make graphs with. Yes, that's correct. What is your name? Chicken of Kinetics or something? Henrietta? That's what your tag says. And so what you remember about y equals mx plus b is that m is the slope. And so what we can see here is that m is negative k. And so if you take this data, you can graph it and figure out your slope, and that is the negative of your rate constant, which is actually really helpful, because then you could say take that rate constant and plug it in here. Or if you've figured out the rate constant from differential, you can take it and plug it in here. And so basically what you end up doing is you use this formula to get a number that you stick in this one, or you use this formula to get a number that you stick in this one. And so that's why they're paired, why they're kind of members of the zeroth order team here. And also your y-intercept, mx plus b, is your a sub 0. So if you had this graph, you could figure out what your concentration was at time 0, and at time t, you can figure out what the concentration is. So these all go together. Also, first order, they all go together, but you're doing ln's, because the ln's allow you to make a straight graph. If you just graph this without the ln's, it's curvy. And that's too bad, because it's really helpful to be able to figure out the slope. So they've kind of manipulated it so that you can make this into a graph and find the slope so that you can get k. So when you have this, you can take the ln of a at time t and the ln of a at time 0 and your rate and time, and that will give you whatever you're missing. And they did this on purpose because this is also y equals mx plus b, and then there's your slope there in the negative k. And we'll be using these, don't worry. And don't worry yet that you don't exactly know how to use this stuff. I'm trying to explain it enough so that when we get to it, you'll be able to use it. And then in a second order, you've got the inverse that matches. So you've got rate equals ka squared, and that's 1 over a a sub t, and 1 over a sub 0. And then the thing to notice about the second order is that your k is positive. Your slope is positive. So this is negative kt, this is negative kt, this is positive kt. That's really important. You've got an upward slope, and you're going to be sticking numbers back and forth between this one and this one, or this one and this one, and it's easy to accidentally forget and put the negative there. But for the second order one, it's positive kt. Then, you can work everything else out. And I'll get to the half-life expressions, I think, on the next page of notes. But these are the, you'll often be asked, well, how long does it take to get down to half of what you started with? And this is just a slightly modified form of these integrated rate laws, where you're finding time at 1/2. So this one is a sub 0, this one is 0.693, by the way, is ln of 2, so it is related. And then this is the inverse one, but you will be using those, don't worry. Flipping back. All right. So here is an example problem of something that you will actually be asked to do, which is they will give you a chart of concentrations over time as your reaction proceeds. And you will be asked, what order is this? Well, that's sort of alarming. And the way that you figure this out is you go, okay, I know that using these graphs, I know that if it is zeroth order and I graph concentration versus time, it will be straight. I know that if it is first order and I graph ln of concentrations versus time, it will be straight. And I know that if it's second order and I graph 1 over concentration versus time, it will be straight. Anything else besides that will be curvy. And so you use your graphing calculator. You use your graphing calculator and the statistics plotting software that's built into your graphing calculator to stick these in and look and see, is it straight yet? And when it is straight, that's the right one. So here are some directions for figuring out how to do this. And also my awesome husband has found me a graphing calculator emulator online. Pull out your calculators and do this with me, seriously, because if you don't, you won't know how to do this. And it's a thing that you need to know how to do. So here is a graphing calculator. Hello, graphing calculator. And the chicken of kinetics is going to peck on it, I suppose. Let's turn it on. Ding. All right. So using, and you'll need to have your that chart that I showed you in front of you because you'll need to be able to use it. All right. And let's see. Let's go back. I'm going to push the buttons that I have listed here in this order to teach you how to use the stat plot function on your graphing calculator. So first I'm going to tell you to hit stat, then hit edit, then hit L1, then I'm just going to kind of run through left to right, top to bottom. This is how you use the stat plot function. So here we go. First you hit the stat button. That's going to get you to this screen. And we need to go and edit our lists. So we're going to choose number 1, edit, and now we have lists. We have list 1, list 2, and list 3. We're only going to use list 1 and list 2. And L1 is going to be your time list, and L2 is going to be your concentration list. So L1 is my time list. I need to type in my times. So that's going to be 0, 20, 40, 60, and 80. Cool. Okay. So that's that. Now for list 2. Uh-oh. Oh, I can't do that. I have to do... What have I done? There we go. Now I need to go over... There we go. I need to go up. This isn't a touch screen. Here we go. And I go over to the right. Now I'm in list 2. And for list 2, that's your concentration. L2 is concentration of N2O5. And that's at the beginning, 0.400, enter. 0.289, enter. 0.209, enter. 0.151, enter. And 0.109, enter. So what we have entered is time and concentration. And what we're going to do is we're going to graph time versus concentration. If we go back to this chart here, we are graphing time versus concentration. And so what we're basically saying by doing this is we're saying if we get a straight line when we do this, we know that the answer is zeroth. So that's what we're checking right now. We're going to go and see if that's right. Where's my calculator? Oh, there it is. We're going to go see that if that's right by going to this thing. You see where it says stat plot above your y equals? You need to get to that by hitting second stat plot. And our stat plots, we have plot 1 off right now, which is too bad, so we need to go and enter in there. It needs to be on. And it needs to be the mountain type. So here's the dots type, here's the mountain type. So let's go to mountain type. Alright. And our X list needs to be L1. And our Y list needs to be L2. And if it isn't, you have to go and change it by hitting second stat, because that gets you to list and it'll allow you to choose which list you want. I'll do that. I'll show that to you. Second stat. And so there's L1. So we go, okay, that's the correct one. Bam. And so now we have told the calculator, this is what I want you to put in your graph. List 1 versus list 2. I want that on, and I want it to be the kind of graph where you go ahead and connect the dots for me. That's the mountain type. And now we need to go make sure that our window is set properly so that we'll be able to see all the X's and Y's. So now you need to go to Window, and our minimum X, which is time, is 0. So that's our minimum X. Our maximum X of time is 80, so let's go to 100 or so. And our X scale needs to be reasonable, so 10 would be pretty good. Y minimum is 0.1, so let's make that 0. Our maximum is 0.4, so let's go up to 0.5. And the scale should be about 0.1. Yep. Alright, now go ahead and hit the graphing button. Uh-oh. The question that we now ask ourselves is that line straight? Is that line straight, chicken of kinetics? No, that is a curvy line. So our hypothesis that this zeroth? If it is, it'll be straight, has shown us it is not zeroth. So now we have to go back and try it for first order. For first order, if it's ln of A, it will make a straight line. So let's go back, stat, and edit our list. And so what we need to do, instead of doing time versus concentration, we need to do time versus ln of concentration. So that's going to be, instead of 0.4, it will be ln of 0.4. Instead of 0.289, it will be ln of 0.289. Instead of 0.209, it's ln of 0.209, etc. ln of 0.151. ln of 0.109. Alright, so this is us hoping that this is a first order reaction, because if it is, this will show up to be a straight graph. We have to go change our window because the second list has changed now. Now it's all negative numbers, so it wouldn't show up in the window that we had set up before. But I believe that our stat plot stuff is all still correct. Yeah, plot 1 on, list 1, list 2, mountain type, we're golden. So now we just got to go to window and change our which one? Our list 2, I think, right? List 2? Change our list 2, which is our Y. Yeah, we need to change our y-axis to reflect these negative numbers. So it needs to go from like -3 to 0. So y -3 to 0. We can scale by ones. All right. Now, if this is a straight line, then it's first order. Dun dun dun. Hey, look at that line. That's straight. Is that straight? That's straight. So, what we have shown is that the graph of time and ln of concentration is a straight line for this data. That means that this data represents a first order reaction. That means, actually, since there's only one reactant, that we now know the differential rate law. It's rate equals K times N2O5 to the first power. So that's kind of cool. So we know that this is the differential thing to use. This is the integrated thing to use. So now we can figure out all sorts of stuff about this reaction. All right, going back. There's my calculator. Where's my notes? There are my notes. All right, so it is first order. Now for the problem. So let's go and do our problem. And I will switch to my black pen screen and work on it. See what you can figure out. All right, so here is problem 1 on the back of the notes, which reads, the reaction between bromate ions and bromide ions in acidic aqueous solution is given by this equation. Determine the orders for all 3 reactants, the overall reaction order, and the value of the rate constant. All right, so we've already discussed doing the first part of this, which is to figure out the order for each of the reactants. And that's doing the method of initial rates. The reason that it's initial, remember, is because if you let it run for too long, it's going to start reaching equilibrium and reacting backwards and forwards, which means that your measurement of a forwards rate is going to get sort of screwy. So for bromate, what you look at is you find an experiment where only bromate changes. And that's comparing experiment 1 to experiment 2. So you've got 0.1 over, well, let's do it the other way. 0.2 over 0.1 equals 2. So that's times 2. And then you compare the rates. You do 1.6 e negative 3 over 8.0 e negative 4. And that equals times 2. So if it's doubled, if bromate is doubled, then the rate is doubled. So in our rate equation here, rate equals the rate constant times bromate. And the question is, what order is bromate? And since bromate is reacting linearly to an increase, it is first order in bromate. Next, we've got to do bromide to find out if bromide is 0th, first, or second order. So we need an experiment in which only bromide is changed. And I believe that is from experiments 2 and 3. Bromate stays the same, hydrogen stays the same, but bromide doubles. So that's 0.2 to 0.1. So when you double bromide, what happens to the rate? You go from to 3.2 e negative 3, 1.6 e negative 3. So that is also times 2. So that means that bromide, the rate reacts linearly to an increase in bromide. So that means that your bromide is first order. And let's look for our next reactant, which is the hydrogen, and that's going to be, let's see, that's going to be experiment 1 to experiment 4. So from experiment 1 to experiment 4, the hydrogen is doubled, and from experiment 1 to experiment 4, the rate goes from 8 e negative 4 to 3.2 e negative 3. So that is quadrupled, and that is more than linear, that is an exponential increase. This is doubling and this is squaring. So that means that hydrogen is squared. So this is our differential rate law for this equation. So the orders for all three reactants are 1 for bromate, 1 for bromide, and 2 for hydrogen ions. What else do we need? The overall reaction order is 1 plus 1 plus 2, so the overall reaction order is 4. And the value of the rate constant, you actually have to stick the numbers in. So let's pick one and solve for k. So let's just do experiment 1, I suppose. The rate is 8e negative 4. K we're trying to solve for. Bromate is 0.1, bromide is 0.1, and hydrogen is 0.1 squared. And you solve for that, and you get k is equal to 0.08. And let's see, the units for this are going to be moles per liter per second equals moles per liter, and moles per liter squared. So this one will cancel this one, and these you'll have to multiply by L. So that's times L cubed, and that's divided by moles cubed. So that's going to be, where's my units? There's my answer. So that's going to be 0.08 moles negative 3 liters third power and seconds negative 1. And if you flip back and look at your notes, that actually continues the trend that we saw in the units, where this chart only goes to third order, but for a fourth order rate law, you would have, you see how the moles go 1, 0, negative 1, negative 2, negative 3, liters negative 1, 0, 1, 2, 3, and always seconds negative 1. So there you have that, and it's important always to have your units for your rate constant. What else do we have? That's that. Okay, so then the next problem is revisiting the example on the notes, the one where we were using our stat function on our calculator to figure out that this is in fact a first order reaction for the decomposition of dinitrogen pentoxide. So the question is, calculate the rate constant for the reaction using the values for concentration and time given in the table, include units with your answer. So we know that for this set of data, the equations that we're using are the first order equations. So let's flip to that. So it's this set of equations that apply, because what we found is that the line was straight when you do an ln, so that means we know that we use this one, and this one. So given, let's see, we've got concentration and time, and we need to find k. So our choices are the differential or the integrated, and since we're given time and concentration, the integrated rate law is going to work here, whereas the differential rate law won't work yet because we don't have rate or k. All we have is concentration. So we're going to go back and use this equation, ln of a sub t equals negative kt plus ln of a 0. So this is the integrated rate law that is used for first order reactions. And let's see, we're trying to find k. Alright, so here's some data points. We can pick any one of them that we want to. We can pick, well, I don't really want to do this one because times 0 is going to give me some funny number. So let's pick time t. Let's pick this last one here. Let's stick that in and see what we come up with. Ln of a at time t are concentration of A is 0.109. We don't know K, but we do know our time. That's 80 seconds. And the concentration of A at time 0 was 0.4. And so what we end up with is subtracting ln of 0.4 off of ln of 0.109 and then dividing by -80, and we end up with K being equal to 0.01625. And then we have to remember what the units are, and since you know that chart of units by now, don't you, chicken of kinetics? We know that for a first order reaction, which this is, the units for K are simply seconds to the negative first power, so or 1 over seconds. All right, so that is how you use the integrated rate law to find K. Then after how many minutes will N2O5 be equal to 0.35? That's going to be 0.35 molar is going to be in here somewhere. Oh, minutes. Ha, that's supposed to be seconds. 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 Whoops. So after how many seconds will N25 be equal to 0.35 molar? That's going to be in here somewhere. So hopefully the answer that we come up with will be between 0 and 20 seconds. And it's asking for time, so we need to use the equation that has t in it, which again is ln of at equals negative kt plus ln of a0, the one that's relevant for first order reactions, which we have learned this one is. And let's see, A at time t is, as they've said, 0.350. K, we now know, negative 0.01625. T, we don't know. And plus, we're getting too small, ln of 0.4. So we subtract ln of 0.4 from 0.35, we divide by negative 0.01625, and we find that time is equal to 8.2 seconds, which is perfect because that is in fact in between 0 and 20 seconds. So we are smart cookies. All right, C, what will the concentration of N2O5 be after 100 seconds have elapsed? Same deal, you go and stick 100 in for T. You know ln of A, you know K, you solve for that. Go ahead and do that yourself. And if your answer is 0.079, you're a smart cookie. D, calculate the initial rate of the reaction, include units with your answer. Now, this is asking for rate. The equation that we have been using, this one here, the integrated rate law for a first order reaction, does not have rate as one of its variables. Isn't that terrible? But its partner, this one, rate equals k times a, does. And as you know, these get used kind of back and forth. We used this one to find k. Now we can take k and plug it in here and find rate. So that's what we're going to do. Use the differential rate law. So rate equals k times a. Calculate the initial rate of the reaction. The rate is 0.01625 times 0.4. So that is initially what our rate is, and that's going to be 0.0065 moles per liter per second. So there you go. And what is the half-life of the reaction? And one thing that you can do is just use this equation here, ln of at equals negative kt plus ln of a0. And I suppose I should pause and define half-life before we do this. The half-life is the time it takes to get to where only half of it is left. So we are looking for t. When they ask for half-life, they're looking for time. We know that k is, actually, that's too close. We know what k is, so that's negative 0.01625. We're searching for t, and ln of a at time 0 is still n of 0.4. ln of a sub t, is going to be, the half-life is when you've used up half. So that's half of 0.4, so that's ln of 0.2. And so then you solve for t. The other thing that you can do here is that you can use the half-life equation, which is the one in this little set here. The half-life equation for a first-order reaction is the time of half, or the half-life time here, is equal to 0.693 over k, which is sort of easier to handle. Remember that 0.693 is ln of 2, which is much more sensible looking than something totally arbitrary like 0.693. It is related, in fact. So t of 1/2 is ln of 2 over k, and you can stick that in and you should get this out no matter which way you did it. There you are. Thanks very much, folks, and I will see you next time.